and we were the winners of the UK CANSAT competition in March. The objective, broadly speaking, is to build a two-wheeled rover which is capable on descent of producing a heat map of the ground below and of measuring humidity, but we'll go through that in a little more detail. First, I'd like to thank our generous sponsors, PCB Train, who are an English company which produces printed circuit boards, and Melexis, a Belgian company which produces integrated circuits, both of whom have been very supportive.
To measure the temperature and pressure, we've taken the MS5637 chip, which measures them digitally, and is very compact, and it has 4 pins, so it's very easy to solder, and the data resolution is optimal.
We're also using the HYT271 to measure external temperature and humidity, and that's also a good choice because it's very reliable, it's compact, and it's factory calibrated, so we didn't have to calibrate it ourselves. And we're using that to investigate changes in dew point as the CANSAT descends, which is the temperature at which water condenses out of the air at constant pressure, because it's important for light aircraft pilots.
Just to expand on that, perhaps it's very important for light aircraft pilots, especially with regard, as I'm sure some of you know, to carburetor icing and wing icing under colder conditions.
The chassis is made from laser cut acrylic and anodized aluminium for extra rigidity, while still staying under the weight limits. There's also an aluminium shell to protect the internal components. The wheels are mounted on the end of the cam, so they have the largest possible diameter, and they're mounted eccentrically to increase ground clearance.
Just to clarify once again, sorry, when he says they're mounted eccentrically, as you can see in this image, the axle is not in the centre of the wheel, which means that as it rotates, it describes a larger circle than it would otherwise. It means that the CANSAT moves in a slightly peculiar way, but it does have the advantage that it increases the ground clearance.
We want you have it with you.
Sorry. No, I'm afraid. Oh, sorry, I've left it down in the hangar. I'm very sorry. But this is taken this morning, so this is up to date. Sorry.
We've also designed a strut which is deployed when the wheels first move after the CANSAT lands, and this helps to make sure that the CANSAT doesn't flip over when it begins to move, which was a problem with our previous design. And here is a video of it in action.
PowerPoint videos. As you can see, it just springs out when the wheel is rotating, which of course we can do through the usual control system. And talking of that control system, I am going to speak briefly about that. I see looks of puzzlement at this graphic on the top, but I can assure you it's really perfectly simple. On the rover, we have a 434 megahertz radio transceiver, which maintains a bidirectional radio link with the ground station. This radio module uses a modulation system called LoRa, which is very resistant to interference as a rule. So that it does mean that the link is a little more robust. For context, I believe the LoRa modems can sustain a signal-to-noise ratio down to something like minus 20 dBm, which is far lower than most competing modules. At the base station, we receive the data. We have an IR camera, a humidity sensor, the other sensors mentioned, and that comes in. We log that in a CSV file, which we can later process using a MATLAB script. And at the same time, we can plot a map. This is a rather crude example, but you can see what this is done live using a Python script, and it simply plot points onto a map image, as you can see. We are also able to send commands the other way, so we can tell the rover to navigate to a point, or indeed to stop or perform some other measurement.
As part of our outreach program, we've done several talks in school to audiences including our engineering society and SBS Space. We've presented talks to parents visiting the school. We also have a website with a regularly updated blog and a Twitter account which posts technical information and comments which has been heard during the trip. We also have a YouTube account which has videos uploaded, including those used in this presentation.
And later, I'll be producing a documentary of our trip here, and that will be useful for outreach next year to encourage interest, so people can see what it's really like to come on a CANSAT trip.
Indeed, to conclude, it is, I think, going to be an interesting project to launch. We've got it more or less ironed out now. I think So fingers crossed, all will be well, and we will be able to tell you of our astounding success later on. Thank you. Oh.
Okay, members of jury, please, questions? I'm sure you will have.
I have, again, the same that the question that I did to the previous presentations. You put some efforts in the downlink station because this is really a single point failure. Are you prepared to, this is robust, you're talking about the robustness of the modulation and that you use, but you can have very robust modulation, but if you don't get the signal, you don't get nothing. So I didn't see any, nothing related to the ground station itself. So how you implemented the ground stations, the links between the CAMs and your...
Would you mind if I use the... sorry, if I just ignore that for a moment. There is a module on the ground which runs in a Python script that communicates via serial here with a receiving module. That is, I suppose, if you wish to consider it as this is the single point of failure here, really. And if that fails, it's somewhat difficult. But because the modulation is because obviously it's not an exclusive modulation, we did consider having the option of a second receiver using a different antenna on a different computer, which seemed to be quite a reasonable suggestion. But we've been quite pressed for time on the development of it, so I
Just one thing, you tested your
Yes.
range?
We tested it, and as I think is mentioned in the final design review, the range, there was no noticeable degradation of signal over an open space range of almost 1.5 kilometres or more, including, and when we went beyond that with some obstructions, it still continued to work.
You did that.
I personally have tested it over a distance in an urban environment for a different purpose with the same modules over a distance of about 2 miles, which is what, 3 or 4 kilometres, and there were no issues with that at a reasonably high data rate.
So I hear something about bit rate, signal to noise ratio, these kind of things, but you did some link budget calculation, for example?
Yes, there are, I believe, some. We used the LoRa. This LoRa modulation is produced by a company called Semtech in China, and they have a link budget calculator, which I used briefly when I did the design originally to check that we would be reasonably, we have a comfortable link margin. With regard to bit rate, there are, I believe, some calculations in the software section of the final design review, to which I think I must point you. I'm afraid I can't remember anything more about it.
We'll take it.
Thank you.
Maybe one. How do you define your mission success? What are your criteria?
The emission criteria, I think, did we not have that there? I'm very sorry,
It's on
I've got
your page 9.
Yes.
the final
Page
design.
9,
Yes, well, I think that would probably be the easiest direction in which to point you, but essentially we've defined a set of mission criteria overall which we wish to accomplish, and we have selected several of the secondary mission criteria. I'm afraid the numbers I can't remember off the top of my head.
1, 3, 4, 5, and 6 from the secondary mission.
Which we are very keen to succeed, and which we will consider the success criteria essentially. Obviously, the primary mission is a must. That's we are accompanying that, I think we showed earlier, using both an internal temperature and an external temperature sensor, so that we can in fact see how much heat is produced by the electronics as a rather pleasant side effect.
Are you planning to launch it with the plane and see, like, test it moving now?
I'm not sure whether we're going to be able to test the movement, because I've been having just this afternoon. I've had some software issues, I think, which are simply I seem to have introduced a bug. But I think we will be doing at least drop test and possibly the electronics. So that remains to be seen.
And you expect to change the coordinates, so make it like a live connection, so moving or
We have a facility that allows us to send WGS-84 coordinates directly to the rover. That then goes into a buffer. I think, thinking about it, would be yes, it's first in, last out, essentially, but of FILO buffer. The waypoints get buffered in, and then at each time you send it, it shunts the existing waypoints along one and puts a new waypoint in. That allows us, essentially, it then navigates roughly to the nearest, directly in a straight line to the nearest waypoint. We did originally want to incorporate some sort of obstacle avoidance, because obviously if you are not in visual contact with the rover, it's difficult to say whether it's going to encounter an obstacle or not. But unfortunately, because of the size and space limitations, it's proved rather difficult in the form factor, unfortunately. But I think it works very well as a, well, I think it works as a proof of concept, essentially, and the idea, exactly, one can of course adjust the size were it to be used for a real, as a model for a real mission of this sort.
Looking forward to it.
So you put your energy in a proof of concept.
I suppose so, yes.
Yeah?
Well,
No?
yes, I think that's fair to say, yes. Are not all of these CANSATs proof of concept, really? Can they really be described as a final, fully formed mission which fulfills all of the criteria which one would necessarily wish to do in a full-sized space mission? I think, well, I'm sure some of the other teams, possibly, I'm afraid we can't claim that.
Very good. Thank you.
Okay, thank you
Thank you very
very
much.
much.